175 meters underground, a machine 17 miles around accelerates particles to a speed so close to light that time itself slows for them. Scientists built it to confirm what they already knew. Instead, they found something the equations say should not be there. A particle wobbling in the wrong direction, a force behaving in ways no model predicts. A universe built almost entirely of things we cannot see, explain, or account for. We will go inside the largest experiment in human history, to the numbers that keep physicists awake, to the anomalies that have survived every attempt to explain them away. If this fascinates you, subscribe and stay with us. Something is hiding in the data. We are only beginning to understand how strange it really is. There is a ring of superconducting magnets buried 175 meters underground, invisible to the millions of people who live and work above it on both sides of the French-Swiss border. The tunnel housing this ring was excavated from solid rock over years of drilling, its circular path laid out with surveying precision so extraordinary that when teams boring from opposite sides of the ring finally met, their tunnel center lines were offset by less than a centimeter over a total distance of 17 miles. The ring houses the most powerful particle accelerator ever built. Two streams of protons travel in opposite directions inside it, each confined to its own beam pipe, guided around the circle by almost 10,000 superconducting electromagnets that must be cooled by liquid helium to -271 degrees Celsius. That temperature is colder than the surface of Pluto. It is colder than the cosmic microwave background radiation that fills all of empty intergalactic space. The liquid helium cooling system is the largest cryogenic system in the world, and it must maintain that extreme cold because the superconducting state of the magnets depends on it. Warm up a superconducting magnet, and it resistively heats. The current in its coils drops, the bending force on the protons decreases, and the whole beam collapses. The system operates continuously during data-taking runs for months at a time. The protons inside this machine are not moving slowly. Each proton has been accelerated through a chain of 4 increasingly powerful machines before it reaches the main ring, gaining kinetic energy at each stage. By the time a proton reaches operational speed in the main ring, it is traveling at 99.9999991% of the speed of light. The gap between that speed and the actual speed of light in vacuum is less than 1 meter per second. This proximity to the cosmic speed limit has a consequence described by Einstein's special theory of relativity. From the proton's own reference frame, time passes at an enormously reduced rate. The 17-mile ring appears contracted to the proton to a distance of only a few tens of meters, and the proton completes its loop in what it experiences as a fraction of a nanosecond. From outside, each proton completes 11,000 laps per second. When the two opposing beams are guided to collide at one of the 4 detector stations around the ring, the concentrated energy at the intersection point reaches 13.6 trillion electron volts in the current operating period. That concentration of energy in a space a trillion times smaller than a living cell recreates conditions from the first billionth of a second after the Big Bang. The particles produced in the collision fly outward in all directions, passing through layers of sensors that measure their positions, momenta, energies, and identities. The detectors do this 40 million times per second, selecting the most interesting events in real time for storage and later analysis. What results is the most comprehensive dataset in the history of experimental physics, and it is full of things that do not fit. The theory against which these measurements are compared is called the Standard Model of Particle Physics. It was assembled over roughly 5 decades of theoretical and experimental work beginning in the late 1960s, when physicists were confronted with a confusing proliferation of newly discovered particles emerging from the first generation of high-energy accelerators. The theoretical work of sorting through this zoo produced a framework of extraordinary power: 12 fundamental particles of matter, organized into 3 generations of 4 particles each, 3 gauge forces, carried by fundamental bosons, and the Higgs mechanism that gives some particles mass, while leaving others massless. The mathematics of the Standard Model is built on gauge symmetries, the same principle underlying quantum electrodynamics, and the resulting predictions match experimental measurements with a precision unmatched by any other scientific theory. The anomalous magnetic moment of the electron has been measured and calculated to 11 decimal places, and they agree. When the Standard Model was being developed, its architects knew they were building something powerful. They also knew they were building something incomplete. It contains no description of gravity. It has 19 freely adjustable parameters that must be measured, not derived. It predicts massless neutrinos, which experiments have since proven wrong. It gives no account of dark matter. It cannot explain why matter dominates antimatter in the universe. These gaps were known. The LHC was supposed to begin filling them. What it has produced is a more precise map of the gaps, with several specific measurements that refuse to fit the model, even within the gaps, where the model should still be right. The first and most celebrated result from the LHC was the discovery of the Higgs boson. The particle had been predicted in 1964 by Peter Higgs in Edinburgh, and independently by François Englert and Robert Brout in Brussels. Their mechanism explained a puzzle in the early electroweak theory. The equations of the weak force required the W and Z bosons to be massless, but they clearly are not. They have masses roughly 100 times greater than a proton. The Higgs mechanism resolved this by proposing that all of space is permeated by a quantum field, now called the Higgs field, that spontaneously breaks the symmetry that would otherwise require the W and Z bosons to be massless. Particles acquire mass by interacting with this background field. The photon has no coupling to the Higgs field and is massless. The top quark has the strongest known coupling and is the heaviest known fundamental particle, roughly 185 times heavier than a proton. The Higgs boson is the quantum excitation of this field, a ripple in the Higgs ocean that permeates all of space, and producing it requires enough energy in a collision to excite the field above its background value. Finding the Higgs boson was the LHC's primary initial mission. On July 4, 2012, CERN held a special seminar broadcast live to universities and laboratories around the world. The spokespersons for the ATLAS and CMS collaborations presented results from their respective analyses of LHC collision data. Both experiments independently reported the observation of a new particle at a mass of approximately 125 giga-electron-volts, with decay signatures matching those predicted for a Higgs boson. The statistical significance in both experiments exceeded 5 sigma independently. In the audience, Peter Higgs and François Englert sat together. Higgs reportedly cried quietly during the presentations. The Nobel Prize followed in 2013, awarded jointly to Higgs and Englert. The Standard Model's final required particle had been found, and the theory stood complete. Physicists celebrated, and they were right to celebrate. But even as the celebration was happening, a problem that had been discussed in theoretical circles for decades became impossible to defer any longer. The Higgs mass of 125 giga-electron-volts is precisely the mass that creates the most acute version of what physicists call the hierarchy problem. In quantum field theory, the physical mass of any particle is not simply its fundamental or bare mass, but includes contributions from virtual particle processes, quantum corrections arising from the constant interaction with the quantum vacuum. For most particles, these corrections are proportional to the particle's own mass and are therefore modest. For the Higgs boson, however, the corrections have a different character. They are proportional to the square of the mass of the heaviest particle that the Higgs interacts with. Through the top quark, which is the heaviest known particle, the quantum corrections to the Higgs mass are enormous. And when the framework extends to very high energy scales, as it must, if the Standard Model is an effective description of a deeper theory that operates at the Planck energy, where gravity becomes as strong as the other forces, the corrections push the Higgs mass toward a value 10 million billion times larger than 125 giga-electron volts. For the Higgs to end up at 125 giga-electron volts, despite corrections pushing it toward the Planck scale, requires that very large positive and negative contributions cancel each other to 34 decimal places of FSA precision. The cancellation is mathematically allowed, but it looks like the universe is balancing a pencil on its tip and has been doing so for 13.8 billion years, and there is no visible hand holding the pencil upright. Something should be explaining the cancellation. Nothing in the Standard Model does. This is the hierarchy problem. The solution that dominated the field for 4 decades was supersymmetry. The idea is elegant. Pair every known particle with a partner of different spin statistics, such that the quantum corrections from the partners precisely cancel the corrections from their Standard Model counterparts. The cancellation is automatic, enforced by the mathematical symmetry itself, requiring no fine-tuning at all. Quarks get partners called squarks, leptons get sleptons, gauge bosons get gaugenos, the Higgs gets the Higgsino. The lightest supersymmetric partner particle would also be stable, electrically neutral, and have a mass in the few hundred to few thousand giga-electron volt range, making it an excellent dark matter candidate. This coincidence, that supersymmetry solves the hierarchy problem, predicts dark matter, and leads to unification of the gauge couplings at high energies, made it the leading theoretical framework for physics beyond the Standard Model for over 30 years. Thousands of papers built on its structure. Experimental physicists at every accelerator, from LEP to the Tevatron, searched for supersymmetric particles. None were found, but the exclusion limits were always lower than the LHC's eventual reach, so the field assumed that the LHC would settle the question. After run 1, no supersymmetric particles had appeared. After run 2, with data at nearly twice the collision energy and several times the total integrated luminosity, still no supersymmetric particles. The lower mass limits on gluons, the supersymmetric partners of gluons, exceeded 2,000 giga-electron volts. Limits on stock quarks exceeded 1,000 giga-electron volts. Across thousands of analyses targeting squarks, gluinos, neutralinos, charginos, and every other sparticle the theory predicted, the result was the same: nothing. The parameter space, where the lightest supersymmetric particles could naturally and without fine-tuning solve the hierarchy problem, is now largely excluded. What survives is either fine-tuned supersymmetry, which defeats the purpose, or supersymmetry at mass scales too high for the LHC to probe, which makes it untestable with current technology. 4 decades of the field's dominant paradigm have been pushed to the margins. The question of what fills the space supersymmetry was supposed to occupy does not have a confirmed answer. While the supersymmetry absence was reshaping the theoretical landscape, a measurement that arrived in April 2022 from a laboratory in the Midwestern United States delivered a different kind of shock. Not a null result, but a positive measurement that disagrees with the Standard Model by a margin that in the entire history of particle physics has never been wrong. The W boson is a massive gauge boson carrying the weak nuclear force, discovered at CERN in 1983. Its mass is predicted by the Standard Model with extraordinary precision through a web of relationships connecting it to other precisely measured quantities. The Z boson mass measured at LEP, the electromagnetic coupling constant measured in low-energy electron scattering experiments, the Fermi constant derived from the precisely measured muon lifetime, and radiative corrections from virtual top quark and Higgs boson loops. All inputs are known to high accuracy. The predicted W mass is 80,357 mega-electron volts per speed of light squared, give or take about 10 mega-electron volts from the theoretical and input uncertainties. Measuring the W mass experimentally to this level of precision at a hadron collider requires extraordinary control of the detector's response to the particles produced in W boson decays, and careful modeling of how the parton structure of the proton, the momentum distribution among the proton's quarks and gluons, affects the kinematics of W boson production. The collider detector at Fermilab collaboration worked for over 2 decades on their measurement, using data collected at the Tevatron Proton-Antiproton Collider during its operational lifetime through 2011. The Tevatron collected collisions at a center of mass energy of 1.96 trillion electron volts, much lower than the LHC, but adequate for precision W mass measurements due to the large W boson production rate and the well-understood detector. The CDF analysis selected roughly 4 million W boson candidate events from trillions of total collisions, applied extensive corrections for detector effects, and used multiple independent techniques to cross-check the result. The systematic uncertainties were estimated and controlled with extreme care over many years. In April 2022, the result was published: 80,433.5 mega-electron volts per speed of light squared, with an uncertainty of 9.4 mega-electron volts. The discrepancy from the standard model prediction is 76 mega-electron volts, and the statistical significance of the discrepancy is 7 sigma. The probability that this discrepancy arises from a statistical fluctuation is approximately 1 in 1 trillion. In the entire history of high-energy physics, a result published with 7 sigma significance in a final, reviewed, and thoroughly scrutinized paper has always represented a real physical phenomenon. 7 sigma is not a threshold exceeded by random noise. It is not exceeded by systematic errors of typical magnitude. Either the CDF analysis contains an error of unprecedented sophistication that has evaded years of internal review and external scrutiny, or the W boson is genuinely heavier than the standard model predicts, and the theory's electroweak framework is wrong in a way that requires new physics. Both possibilities are extraordinary. The first would be the most significant analysis error in the history of precision measurements. The second would be the most important experimental result since the discovery of the Higgs boson. The subsequent measurement from the ATLAS experiment at the LHC, using a different detector, a different collision system, and different analysis techniques, returned a W mass consistent with the standard model and inconsistent with CDF. 2 of the most carefully operated experiments in particle physics disagree by more than 4 sigma. The resolution of this disagreement, which will arrive from additional measurements at CMS and LHCb in the coming years, will be one of the defining moments of the current era of particle physics. And while the W boson debate occupied conference rooms and journals, another experiment was pursuing a measurement of a completely different character, targeting not the mass of a particle, but the rate at which a particle spins in a magnetic field, and finding an anomaly that has survived more than 2 decades of increasingly precise measurement. The muon is a particle that exists throughout everyday life without most people ever thinking about it. Cosmic rays, high-energy protons, and heavier nuclei originating from supernova remnants and other violent astrophysical sources continuously rain down on the upper atmosphere of the Earth. When these primary cosmic rays strike air molecules, they produce showers of secondary particles, including large numbers of muons. These muons rain down on the surface, passing through the roofs and floors of buildings, through people, through meters of rock or water, at a rate of roughly 2 per square centimeter per minute at sea level. They do so almost without interaction because they participate only in the weak force and electromagnetism, and at their typical cosmic ray energies, they lose energy slowly and traverse large amounts of material before decaying. Every second, about 200 muons pass through the area of your body from above. They do this silently, invisibly, harmlessly. They are the most common energetic charged particles reaching the Earth's surface from space and their precisely known properties make them useful probes of fundamental physics. The muon's magnetic moment is among the most precisely known quantities in physics. In a magnetic field, the muon's spin axis precesses around the field direction at a rate governed by the magnetic g-factor, a dimensionless number that quantum mechanics predicts should differ from its classical value of exactly 2 by a tiny amount arising from virtual particle processes. The calculation of this tiny deviation requires summing contributions from every virtual particle process the muon can undergo. Virtual photon emissions and reabsorptions contribute the dominant correction. Virtual electron loops contribute slightly less. Virtual W and Z boson processes contribute more. Virtual quark and gluon loops, the so-called hadronic vacuum polarization contribution, are harder to calculate but known to reasonable precision. The total standard model prediction for the muon anomalous magnetic moment has been refined over decades by multiple independent groups and is known to 11 significant figures. Measuring it to matching precision requires storing muons in a precisely uniform magnetic ring and measuring the tiny difference between the rate at which their momentum direction curves around the ring and the rate at which their spin direction precesses. Any particle or force not in the standard model that the muon interacts with, even one too heavy to be produced at any existing accelerator, would alter this tiny difference by a calculable amount. The storage ring used for this measurement, a 50-foot diameter superconducting magnet weighing 17 tons, was built at Brookhaven National Laboratory in the early 1990s and ran the first measurements of the muon G2 from 1997 to 2001. By 2004, the combined Brookhaven result showed a roughly 3 sigma deviation from the standard model prediction. Intriguing, but not definitive. The decision was made to move the experiment to Fermilab outside Chicago, where higher intensity muon beams and better infrastructure would allow more precise measurements. The problem was the storage ring itself. It was a single, continuous, superconducting magnet that could not be cut, disassembled, or shipped in pieces without compromising its precision. It had to travel intact. The solution was to place it onto a specially built flatbed barge, float it from Long Island through the Intracoastal Waterway, around the tip of Florida, across the Gulf of Mexico, up the Mississippi River, and finally up the Illinois River to a dock near Fermilab. The transport took 35 days and required careful management of ocean swells, river currents, and weather conditions that could stress or jostle the magnet. From the river dock, the ring was trucked overland to the Fermilab campus in an overnight operation conducted between 1 and 5 inches the morning to avoid traffic, requiring the temporary removal of highway signs, traffic signals, and tree branches along the route. The entire operation was covered by news media across the country. It was one of the most remarkable logistics achievements in scientific history, and it succeeded without damaging the magnet. At Fermilab, the upgraded Muon G2 experiment ran with improved electronics, more precisely controlled magnetic fields, and substantially larger muon samples. Results published in 2021 confirmed the Brookhaven deviation at approximately 3.3 sigma. Results published in 2023, with more data, pushed the combined Brookhaven plus Fermilab significance to approximately 5 sigma. The muon's measured magnetic moment exceeds the standard model prediction. Something is interacting with the muon in its quantum environment that the standard model does not include. It has never been directly observed. It is too heavy to be produced at existing accelerators, or it interacts too weakly to be detected directly, or both. But it is there, reliably, reproducibly, at 5 sigma significance, in the quantum foam that surrounds every muon during its brief 2 microsecond life. The interpretation carries a complication. In 2023, the BMW collaboration published a lattice quantum chromodynamics computation of the hadronic vacuum polarization contribution that yielded a substantially different result from earlier calculations using electron-positron collision data. If the BMW calculation is correct, the standard model prediction for the Muon G2 is larger than previously estimated, which would partially close the gap with the experimental value. The physics community is currently working intensively to reconcile the two approaches, since they use fundamentally different methods to calculate the same physical quantity, and they give different answers. Several intermediate approaches and cross-checks are being pursued simultaneously until the theoretical controversy resolves. The experimental result is clear, and the theoretical prediction is uncertain. But the muon has not changed its behavior. The wobble is real. While the Muon experiment tracked quantum effects in a storage ring in Illinois, the LHCb experiment at CERN was tracking different quantum effects in billions of B-meson decays. And for several years, the data told a story that looked like a direct violation of a principle the standard model holds as fundamental. The LHCb detector is a specialized instrument, unlike the general-purpose ATLAS and CMS detectors. It is built in a forward geometry, pointing mostly along the beam direction, because B-mesons produced in proton-proton collisions at the LHC tend to fly forward due to the kinematics of bottom quark production. The detector is optimized to identify B-mesons by their displaced decay vertices. Since B-mesons travel a few millimeters before decaying, a distance large enough for the silicon tracking detector to resolve with high efficiency, the experiment records the decay products of hundreds of millions of B-mesons per year and analyzes their decay modes with extraordinary precision. Among the most important measurements LHCb performs are comparisons between decay rates to final states involving muons and electrons. The standard model contains a symmetry called lepton universality. The electron, muon, and tau leptons are structurally identical to the standard model's forces, differing only in mass. At the energy scales of B-meson decays, these mass differences are negligible. Lepton universality therefore predicts that the rates of B-meson decays to muon pairs should equal the rates of equivalent decays to electron pairs to very high precision. The ratio RK, measuring the rate of B to K plus muon anti-muon divided by B to K plus electron-positron, should be essentially 1. Starting in 2014, LHCb published measurements of RK and the related ratio RK star that were consistently below 1. With each data update, the significance grew. By 2021, the combined significance of the deviation from lepton universality across multiple measurements was approaching 3 sigma. Theoretical papers appeared in large numbers proposing leptoquarks, particles that couple quarks directly to leptons and could preferentially affect muons relative to electrons, and new gauge bosons called Z-prime particles that would mediate a new force distinguishing between muon and electron interactions. In 2022, LHCb corrected an error in their electron reconstruction simulation. The Monte Carlo model, used to simulate how electrons move through the detector material, had underestimated the rate at which electrons emit photons through bremsstrahlung, causing the simulation to overestimate the electron detection efficiency. Correcting this systematic effect brought RK and RK star back to values consistent with 1, consistent with lepton universality, consistent with the standard model. The correction was made transparently, the updated results were published, and the apparent anomaly disappeared. What did not disappear was the P5, prime observable, an angular distribution parameter measured in the same B-meson decay channel. This quantity has shown a roughly 3 sigma tension with standard model predictions since it was first measured in 2013. It has been updated with more data in 2015, 2020, and subsequently, and the tension persists. The theoretical interpretation of this tension is complicated by hadronic uncertainties, the same difficulties in calculating the strong force contributions that complicate the G2 interpretation, and no consensus has emerged on whether the tension reflects new physics or an underestimated theoretical uncertainty. But the tension has been present for over a decade, across multiple datasets, and has not been attributed to any identified systematic error. It is pointing somewhere. Whatever it is pointing to, it has been stubbornly present long enough to be taken seriously as a potential signature of physics the standard model does not contain. The P5 prime tension that persists in LHCb data is significant, partly because of where it sits in the broader experimental landscape. B-meson physics has historically been a reliable arena for indirect discovery. The mixing of neutral B mesons with their antiparticles was first measured precisely at Clio and Argus in the late 1980s, and the rate of mixing was used to constrain the mass of the top quark well before it was directly discovered. The amount of CP violation in B meson decays, measured with extraordinary precision by Babar and Bell, confirmed the CKM framework and allowed the complex phase of quark mixing to be determined. These measurements were not searching for exotic new physics, but for the internal consistency of the standard model, and they found it to great precision. The fact that the same system is now showing persistent tensions at the 3 sigma level in angular observables that are sensitive to short-distance physics deserves to be interpreted against that backdrop. When B-meson physics gave accurate indirect information about the top quark, that information was eventually confirmed by direct discovery. If the P5 prime tension reflects something real, direct confirmation through either a leptoquark discovery at the LHC or a higher significance measurement in a future flavor experiment will eventually arrive. The LHCb collaboration is planning a major upgrade of its detector for the Run 4 and Run 5 periods of LHC operation. The upgraded detector, sometimes called Upgrade 2, is designed to operate at luminosities significantly higher than the current detector can handle, exploiting the full collision rate of the high luminosity LHC to accumulate B-meson datasets roughly 100 times larger than any currently available. With that statistics increase, measurements currently at 3 sigma significance will either rise to discovery level or dissolve entirely. The upgrade is technically challenging, requiring new silicon tracking detectors, improved particle identification systems, and faster data acquisition electronics. But its physics motivation is clear. The angular anomalies in B-meson decays are at exactly the sensitivity level where more data is the decisive factor, and the high luminosity LHC era will provide that data if the hardware can handle it. Understanding what is happening in B-meson decays requires better experimental data and better theoretical calculations. The hadronic uncertainties in the P5 prime observable arise from the difficulty of computing the contributions of the strong force to the matrix elements that relate the B-meson initial state to the final kaon and lepton pair state. These matrix elements involve non-perturbative QCD effects that cannot be calculated analytically. They can be estimated using QCD sum rules, which are analytical approximations valid in specific kinematic regimes, or using light cone sum rules, or using lattice quantum chromodynamics on a computer. Different groups using different methods get different answers. The spread among the different estimates contributes the dominant systematic uncertainty in interpreting the experimental deviation. The ongoing improvement of lattice QCD calculations, driven by increasingly powerful supercomputers and improved algorithms, is expected to reduce this uncertainty substantially in the coming decade. When the theory uncertainty is reduced to the level of the experimental precision, the question of whether the P5 prime deviation represents new physics will have a much cleaner answer. The combination of improved data from LHCb Upgrade 2 and improved theory from Lattice QCD represents the most systematic path toward resolving the B-meson anomalies. It is a path that takes years, requires large computing resources, and demands continuous cross-checks between different theoretical approaches. But it is the path that particle physics has always taken to convert experimental hints into confirmed discoveries or definitive exclusions. the same process that confirmed the CKM picture of CP violation through years of Babar and Bell measurements, and then refined it through LHCb, is now being applied to the anomalies that suggest the CKM picture may be incomplete beyond the specific B meson observables. The LHCb experiment has an expanding physics program that touches almost every aspect of flavor physics. It measures charm hadron properties with world-leading precision, studies the spectroscopy of excited B and D meson states, searches for exotic hadrons made of more than 3 quarks, and probes the properties of baryons containing heavy quarks. In 2021, LHCb reported evidence for doubly charmed tetraquarks, exotic hadrons containing 2 charm quarks and 2 lighter antiquarks, in a configuration forbidden in the naive quark model that describes protons and neutrons. The observation was subsequently confirmed and extended to additional states. These exotic hadrons are not new physics beyond the standard model, but they reveal rich aspects of quantum chromodynamics at low energies that are incompletely understood. The strong force has surprises to offer even within the standard model, and the LHCb detector is finding them. While flavor physics accumulates anomalies and exotic hadrons in the precision domain, the highest energy collisions at ATLAS and CMS are providing the most precise characterization of the Higgs boson ever achieved. Since its discovery in 2012, the Higgs boson has been measured in all its major decay channels. It decays to 2 photons, 2 Z bosons, 2 W bosons, 2 tau leptons, and 2 bottom quarks, with rates that can be compared against standard model predictions, expressed as ratios called signal strengths. All measured signal strengths are consistent with the standard model within the current experimental precision. The Higgs appears to be exactly what the standard model predicted, a single scalar particle whose couplings to other particles are proportional to those particles' masses, with no significant anomalous contributions. But the current precision, typically at the 10 to 20% level for individual decay channels, leaves substantial room for new physics to hide. A new particle, or force, that modifies the Higgs couplings by 5% would be undetectable with current data, but would be within reach of the high luminosity LHC's precision program. The Higgs boson is a direct probe of the electroweak symmetry breaking mechanism, and any deviation in its couplings from standard model predictions would indicate that the symmetry breaking mechanism is not exactly as described. Extensions of the standard model that include additional Higgs doublets, Higgs singlets, or composite Higgs structures all predict deviations in the Higgs couplings at the few percent level. The LHC's precision Higgs program is steadily narrowing the allowed room for such deviations, and the high luminosity LHC will narrow it further. If new physics modifies the Higgs sector, the high luminosity LHC's Higgs measurements will see it. The top quark, the heaviest known fundamental particle, plays a special role in the hierarchy problem and in the quantum corrections to the Higgs mass. Its large coupling to the Higgs field makes it the dominant source of the quantum corrections that push the Higgs mass toward the Planck scale. Supersymmetry's solution to the hierarchy problem works through the stop quark, the top quark's supersymmetric partner, cancelling the top quark's large correction with an equal and opposite contribution. The absence of the stop quark in LHC data is therefore particularly troubling for the naturalness argument. The particle most responsible for the hierarchy problem's severity has no confirmed partner to cancel its effect. Precision measurements of the top quark mass and its coupling to the Higgs boson are being pursued at high priority in Run 3 and the high luminosity LHC program, both because they test the standard model's consistency and because they constrain the models that would naturally explain the hierarchy. The Higgs boson's discovery validated the standard model's symmetry breaking mechanism, but it also opened new questions about the Higgs sector's completeness. The standard model contains a single Higgs doublet, producing one physical Higgs boson after electroweak symmetry breaking. Many theoretical extensions contain 2 or more Higgs doublets, leading to a richer spectrum of scalar particles. 2 neutral scalar Higgs bosons, one neutral pseudoscalar Higgs, and a charged Higgs pair. These additional Higgs particles would modify the properties of the observed 125 giga-electron volt Higgs boson and would produce new signatures in LHC data. The searches for additional Higgs bosons at the LHC span a wide range of mass and decay mode, from the charged Higgs producing top quarks and bottom quarks at masses of a few hundred giga-electron volts to heavy neutral Higgs bosons decaying to tau pairs or bottom quark pairs. All searches have returned results consistent with background, setting limits that rule out large portions of the parameter space in generic 2 Higgs doublet models. The exception is the excess in the d-tau channel near 100 giga-electron volts observed in Run 3 data by both ATLAS and CMS. If this excess is real, it would be the first evidence for a new Higgs-like particle produced through gluon fusion and decaying to 2 tau leptons. The rate of this hypothetical signal is consistent with what would be expected from a light pseudoscalar Higgs boson in a supersymmetric model where the supersymmetric particles are too heavy to solve the hierarchy problem, but the additional Higgs sector is accessible at lower mass. The Run 3 data are being analyzed as rapidly as possible to determine whether the excess grows with more data or dissolves. If it survives and reaches 5 sigma significance, it will be the most important particle physics discovery since 2012. The measurement of the strong coupling constant at the LHC provides another precision test of the standard model that connects to multiple outstanding equations. The strong coupling constant, which describes the strength of the strong nuclear force, runs with energy. It decreases as the energy scale increases, reflecting the asymptotic freedom of quantum chromodynamics. Precise measurements of the strong coupling at different energy scales test whether this running is exactly as the standard model predicts, and whether it extrapolates smoothly to the grand unification scale, where all 3 gauge couplings are predicted to converge in supersymmetric extensions of the standard model. The LHC measurements of the strong coupling at energies of hundreds to thousands of giga-electron volts are consistent with the standard model prediction and provide increasingly precise constraints on physics beyond the standard model through their effects on precision electroweak observables. One of the most subtle and revealing tests of the standard model at the LHC concerns the self-coupling of the Higgs boson. The Higgs potential, the mathematical description of the Higgs field's energy as a function of its amplitude, has a specific shape in the standard model, with a minimum at a non-zero field value that drives electroweak symmetry breaking. The shape of the potential is determined by the Higgs mass and the Higgs self-coupling, which governs how strongly the Higgs boson couples to itself. Measuring the Higgs self-coupling requires observing the production of 2 Higgs bosons in a single collision, a process called Higgs pair production. This process is extremely rare in the standard model, happening only a few times per trillion collisions at LHC energies, and the 2 Higgs bosons produce a challenging signal that must be separated from much larger backgrounds. Current LHC data do not yet have sufficient sensitivity to measure the Higgs self-coupling precisely. The high-luminosity LHC, with its tenfold increase in data, should achieve the first significant constraints on the Higgs self-coupling. Any deviation from the standard model prediction would indicate that the shape of the Higgs potential is different from the simplest prediction, potentially providing a clue about the nature of the electroweak phase transition and whether it could have been a first-order transition capable of generating the matter-antimatter asymmetry. These precision measurements, taken together, form a comprehensive program aimed at characterizing the Higgs sector with the same thoroughness that LEP characterized the Z boson sector in the 1990s. The Z boson was measured in millions of decays at LEP, and the resulting precision tests of the electroweak sector constrained the masses of the top quark and Higgs boson before either was discovered. The Higgs boson is now being measured in billions of events at the LHC and high-luminosity LHC, and the resulting precision will constrain the masses and couplings of particles beyond the standard model in the same way. The program is ongoing, The standard has been set by LEP. The LHC and its successors will meet it. These threads converge on a single defining fact about experimental particle physics in the current era. The standard model is correct to high precision, but it is not complete, and the evidence for its incompleteness is specific, quantitative, and growing with every year of LHC operation. The anomalies are not artifacts of poor statistics or sloppy analysis. They are the outputs of the most sophisticated measurement programs ever run, at the most powerful instrument ever built, analyzed by thousands of physicists using the best available techniques. They persist, they deepen, and they point consistently toward a level of physical reality just beyond the reach of current instruments, waiting for the next generation of machines to confirm what the current generation has already begun to see. The standard model is the most successful approximate description in the history of science. The physics beyond it is the most important open question. Both of these things are true simultaneously, and neither cancels the other. The P5 prime anomaly in B meson decays is not the only place where the LHCb dataset shows a tension with standard model predictions. It is the most durable, the one that has survived the most scrutiny over the longest period, but the broader pattern of B meson results at LHCb forms a consistent landscape of deviations that collectively point toward the same region of theoretical parameter space. B mesons and their decays probe the flavor structure of the standard model at a level of precision that complements direct production searches at ATLAS and CMS. When a B meson decays through a flavor-changing neutral current, a process where the bottom quark transforms into a strange quark while emitting a lepton pair, the rate and angular distribution of that decay are sensitive to any new particles that might contribute through virtual loops. The standard model predicts these rates and distributions with calculable precision, but the hadronic uncertainties from strong force contributions are significant and difficult to estimate reliably. Multiple measurements of multiple observables in multiple decay channels at LHCb show deviations that, when combined, point toward a consistent modification of the effective coupling constants, describing how quarks interact at loop level. Whether this pattern represents new physics or a systematic failure of the hadronic calculations is the central unresolved question in B physics today, and it is a question that the LHC's expanded Run-3 dataset and improved theoretical calculations are being deployed to answer. The theoretical significance of the persistent B meson anomalies goes beyond the specific observables themselves. They connect to a broader program of using rare, loop-level processes to probe mass scales far above what colliders can directly produce. Before the top quark was directly discovered at Fermilab in 1995, its mass had been constrained to within a predictive range by indirect measurements of B meson mixing at LEP and earlier experiments. Before the Higgs boson was directly produced at the LHC, in 2012, its mass range had been narrowed by electroweak precision measurements at LEP and the tevatron through the virtual contributions of the Higgs to loop processes. The indirect constraints were accurate because the standard model's equations link all particle properties together through loop corrections, allowing measurements of one particle's properties to constrain the masses and couplings of particles not yet directly produced. The B meson angular anomalies may be performing the same function for a new particle at several trillion electron volts, too heavy for the current LHC to produce directly, but leaving its fingerprint on the rare decays of B mesons produced in enormous quantities. The answer will arrive with more data and more precise calculations. The pattern has been there long enough to deserve that investment. A far grander question overshadows all the specific anomalies and all the specific measurements in the LHC dataset. It is the question that sits behind everything particle physics is trying to understand. Why does the universe contain matter at all? This is not a rhetorical or philosophical question. It is a precise physical question with a specific quantitative answer demanded by the observations and an equally specific answer from the standard model that falls catastrophically short of what is required. When the Big Bang occurred, approximately 13.8 billion years ago, the energy that burst into existence took the form of radiation and of matter-antimatter pairs, continuously created and annihilated. The laws of quantum field theory governing particle creation are symmetric, under the exchange of particles and antiparticles. Every quark produced by a photon was accompanied by an antiquark, every electron by a positron, every neutrino by an antineutrino. The creation process cannot favor one over the other without a violation of the fundamental symmetry of the equations. In the extraordinarily hot early universe, particles and antiparticles were created at the same rate and annihilated at the same rate. The total balance was maintained by the symmetry of the interactions. As the universe expanded and cooled, particle-antiparticle pairs stopped being thermally created, but continued to annihilate when they met. The final state of a perfectly symmetric universe would contain only photons, the radiation left over from the total annihilation of all matter and antimatter. No protons, no electrons, no atoms, no molecules, no chemistry, no biology, no telescopes or particle accelerators. Nothing but a cooling sea of light spreading through empty space forever. The universe is not empty. Every telescope that has been pointed at the sky confirms that matter dominates at every scale we can probe. Dozens of surveys searching for antimatter in the form of antiprotons, antinuclei, or antistars have found essentially none in the observable universe. If significant antimatter existed in cosmic quantities, the boundaries between matter and antimatter regions would produce intense gamma-ray emission from annihilation. No such emission is observed. The observable universe is made almost entirely of matter. The ratio of surviving matter to the photons left over from the annihilations is approximately 1 baryon per billion photons. For every billion matter-antimatter pairs that annihilated, one extra matter particle remained. 1 in a billion. Everything is made of those survivors. The standard model contains a mechanism that can produce this kind of asymmetry. It is called CP violation, the violation of the combined symmetry of charge conjugation and parity reversal. Under perfect CP symmetry, replacing all particles with antiparticles and all spatial coordinates with their reflections would leave all physical processes unchanged. CP violation means this symmetry is broken. Some processes proceed at different rates for particles than for their antiparticles. This difference is a prerequisite for generating a matter excess. CP violation was first observed experimentally in 1964 by James Cronin and Val Fitch at Brookhaven, who found that neutral kaons exhibited slightly different decay patterns than neutral antichacons. The discovery, initially mysterious, was eventually incorporated into the standard model through the theoretical work of Makoto Kobayashi and Toshihide Masukawa, who realized that CP violation arises naturally if there are at least 3 generations of quarks through a complex phase in the quark mixing matrix. Their prediction was confirmed when the charm quark and the bottom and top quarks were subsequently discovered, completing the 3 generations required. The experimental verification of CP violation has been systematically extended over subsequent decades. The Babar experiment at the Stanford Linear Accelerator Center and the Bell experiment at the High Energy Accelerator Research Organization in Japan were built specifically to study CP violation in B meson decays, both measuring the asymmetry between B meson and B antimeson decay rates to various final states with extraordinary precision. Their combined results confirmed the CKM picture of CP violation in B meson decays and measured the complex phase that governs it. In 2019, the LHCb experiment announced the first observation of CP violation in D meson decays, particles containing charm quarks, showing that matter and antimatter D mesons decay to certain final states at slightly different rates. This completed the experimental verification of CP violation across all 3 generations of quarks in the Standard Model. And then the calculation. The Standard Model's total CP violation, from all known sources combined, is insufficient by many orders of magnitude to generate the observed matter-antimatter asymmetry of the universe. The problem is not subtle. Detailed calculations of electroweak baryogenesis, the process by which the matter excess would have been generated during the electroweak phase transition, when the Higgs field settled into its current vacuum state, show that the Standard Model's CP violation is approximately 10 billion times too small to produce the required asymmetry. The electroweak phase transition in the Standard Model is also too smooth, a crossover rather than a first-order phase transition, for the baryogenesis mechanism to operate efficiently even if the CP violation were large enough. The Standard Model simply cannot explain why matter dominates. It cannot explain why the universe is not empty. There must be additional CP violation in processes involving particles or forces not yet discovered that operated during the first fraction of a second of the universe's existence and created the asymmetry that everything subsequently built on. Finding those sources of extra CP violation is one of the highest priority goals of particle physics. So far, they have not been found. While the matter-antimatter asymmetry demands new CP-violating physics that has never been directly observed, a different class of invisible physics manifests at every scale of the cosmos through its gravitational effects. Dark matter is real. It is abundant. It is measurably present in every galaxy and every galaxy cluster, shaping the structure of the observable universe from its earliest moments. It is also completely unidentified, despite decades of intense experimental searching that has eliminated the most theoretically motivated candidate across the bulk of its expected parameter space. The evidence for dark matter's gravitational existence is so robust and comes from so many independent directions that the phenomenon cannot reasonably be doubted. The rotation curves of spiral galaxies, first systematically measured by Vera Rubin and Kent Ford, beginning in the 1970s, show that the orbital speeds of stars in the outer regions of galaxies do not decline with distance from the galactic center, as they would if the visible matter were all there is. The curves are flat. This flatness is precisely what would be expected if each galaxy were embedded in a diffuse, roughly spherical halo of invisible mass extending far beyond the visible disk. Rubin and Ford's measurements covered dozens of galaxies with the same result in each case. The flat rotation curve is a universal property of spiral galaxies. Gravitational lensing provides independent evidence on larger scales. The bending of light by gravity, predicted by general relativity and confirmed during a 1919 solar eclipse, allows the total mass along a line of sight to be measured from the distortion it induces in background images. Galaxy cluster lensing measurements consistently return total masses several times larger than the combined mass of all visible stars and hot X-ray emitting gas in the clusters. The invisible component, dark matter, makes up roughly 85% of the cluster mass. The bullet cluster, the collision remnant of 2 galaxy clusters that passed through each other roughly 150 million years ago, provides what is perhaps the most direct evidence that dark matter is a physical substance, rather than a modification of gravity. In the collision, the hot gas from each cluster was slowed by electromagnetic interactions, while the dark matter halos passed through each other gravitationally undisturbed. Gravitational lensing maps of the system showed 2 separated mass concentrations offset from the hot gas, corresponding to the diverged dark matter halos. The spatial separation of the mass from the gas is direct observational evidence for a non-baryonic form of matter that interacts primarily through gravity. The cosmic microwave background encodes the dark matter abundance with high precision. The temperature fluctuations in this ancient light reflect acoustic oscillations in the plasma of the early universe, and the positions and heights of the acoustic peaks in the power spectrum depend sensitively on the relative abundances of ordinary matter, dark matter and radiation. The Planck satellite measured these fluctuations with extraordinary precision and determined that dark matter constitutes roughly 26.8% of the total energy of the universe, while ordinary matter, protons, neutrons, electrons, everything made of quarks and leptons, constitutes only 4.9%. Dark matter is not a minor correction. It is the dominant form of matter, 5 times more abundant than everything that has ever been directly observed. What dark matter is made of remains the central question. The WIMP hypothesis dominated the field for 30 years, driven by the coincidence between the mass range where supersymmetric partner particles were predicted and the mass range where thermally produced dark matter would naturally achieve the correct cosmological abundance. The LHC searched for WIMPs through missing transverse energy signatures across hundreds of different event topologies over 12 years of operation. Underground direct detection experiments searched for the nuclear recoils that WIMPs would occasionally cause in multi-ton detectors buried under kilometers of rock. Neither search found a confirmed signal. The simplest, most natural supersymmetric WIMP candidates are now largely excluded. The WIMP miracle was coincidental in a way that turned out not to indicate what physicists thought it indicated. The field is now exploring a much wider range of dark matter candidates, from ultralight axions oscillating as a coherent field to primordial black holes formed in the early universe, none of which has yet been confirmed. The WIMP's absence at the LHC has a specific significance beyond the dark matter question. It was supposed to show up as part of the supersymmetric spectrum. Squarks and gluinos were supposed to decay to the lightest supersymmetric particle, the WIMP candidate, through long chains of intermediate particles, producing events with multiple jets, possibly leptons, and large missing transverse momentum pointing at the escaped dark matter particle. These events were searched for in thousands of analysis configurations. The limits on the sparticle masses climbed year after year. The territory where the simplest supersymmetric models could simultaneously solve the hierarchy problem and provide a WIMP dark matter candidate has been eliminated. The two most compelling arguments for supersymmetry, the hierarchy problem and the dark matter, have been tested, and the predicted solutions have not appeared. Whatever comes after the standard model must solve these problems in a different way. In December 2015, the LHC briefly seemed to offer a glimpse of that something else. The first data from Run 2 at the new energy of 13 trillion electron volts included a tantalizing bump in the diphoton spectrum at approximately 750 giga-electron volts, seen independently by both ATLAS and CMS. ATLAS measured a local significance of 3.9 sigma. CMS measured 2.6 sigma. The coincidence between two independent experiments at the same mass in the same channel was precisely the kind of pattern that physicists are trained to notice. The theoretical community responded at a scale unprecedented in the field. Papers appeared at 15 to 20 per day. Within a month, over 100 papers had been written. By August 2016, when ATLAS and CMS released updated results with 3 times as much data, more than 500 theoretical papers existed about a particle that had not yet been confirmed as real. The updated results showed a smooth, background consistent spectrum at 750 giga-electron volts. The excess had been a statistical fluctuation. 2 experiments had independently fluctuated upward at the same mass by coincidence, a coincidence made more likely by the large number of mass bins and decay channels being searched simultaneously. 500 papers remained as artifacts of noise. The episode was sobering. It exposed the psychological state of a field that had spent years searching for new physics and finding none, and in that state had lowered its threshold for excitement below where it needed to be. The 5 sigma discovery standard exists precisely to prevent exactly this kind of misstep. The physics community absorbed the lesson and tried to apply it more rigorously in subsequent analyses. What the LHC reliably creates, reproducibly and in controllable conditions, is something far more extraordinary than a particle bump in a spectrum. In heavy ion mode, with lead nuclei colliding at full energy, the machine recreates the most extreme state of matter in the accessible universe, and that state has revealed connections between the most powerful accelerator on Earth and the mathematics of black holes that no one anticipated. Lead-lead collisions at the LHC involve nuclei each containing 82 protons and 126 neutrons, for 208 nucleons per nucleus. Each nucleon contains 3 quarks. When 2 of these massive nuclei collide head-on at full LHC energy, the energy deposited in the nuclear overlap region briefly reaches temperatures exceeding 4 trillion degrees Celsius. For comparison, the surface of our nearest star is roughly 5,500 degrees. The stellar interior is roughly 15 million degrees. A detonating nuclear weapon reaches roughly 100 million degrees. The peak temperature of a core collapse supernova reaches roughly 100 billion degrees. The quark-gluon plasma created in a lead-lead collision at the LHC reaches 4 trillion degrees, 250,000 times hotter than the stellar interior, and existing in a volume roughly 1 trillion times smaller than a single proton for a duration roughly 10 to the power of -23 seconds. At that temperature, the binding energy of the strong force is overwhelmed by the thermal energy. Quarks and gluons that are ordinarily confined inside protons and neutrons break free and flow together as a single substance. This quark-gluon plasma is not exotic or speculative. It was the normal state of all matter in the universe for the first 10 microseconds after the Big Bang. The LHC recreates it in a laboratory, studies its properties in detail, and extracts information about the fundamental nature of the strong force that cannot be obtained in any other way. The plasma's most astonishing property is how it flows. Theoretical calculations based on asymptotic freedom, the weakening of the strong coupling at high energies and short distances, predicted that at the extreme temperatures of the quark-gluon plasma, the quarks and gluons would interact relatively weakly and the plasma would behave roughly like a gas. The viscosity of a weakly coupled gas is relatively high because the particles travel long distances between collisions and efficiently transport momentum across the fluid. The LHC measurements told a completely different story. Elliptic flow measurements, which capture the degree to which the initial geometric asymmetry of an off-center collision is converted into a preferred direction of particle emission through the collective expansion of the hot plasma, showed that the quark-gluon plasma flows almost without internal friction. Its viscosity to entropy density ratio approaches the theoretical minimum derived from the AD-CFT correspondence, a mathematical result in string theory that maps the behavior of strongly coupled quantum field theories to the physics of black holes in higher dimensional spaces. The minimum value of this ratio is a universal constant involving Planck's constant divided by Boltzmann's constant, predicted by string theory to be the ultimate lower bound on any physical fluid's internal friction. The quark-gluon plasma at the LHC approaches this bound more closely than any other substance ever measured, including superfluid helium, cooled to within thousandths of a degree of absolute zero. The mathematics developed for studying hypothetical black holes in 5-dimensional spaces describes, with remarkable accuracy, the flow of hot matter in a lead-lead collision at the world's most powerful accelerator. This was not in any physicist's plan. It emerged from the data. The further shock came from proton-proton collisions. In high multiplicity proton-proton events at the LHC, the subset of collisions that produce unusually many secondary particles, the CMS experiment found long-range azimuthal correlations between pairs of particles. 2 particles produced at very different positions along the beam direction were correlated in their azimuthal angle, the angle around the beam axis, in a way that is the defining signature of collective flow in heavy ion collisions. This correlation, called the ridge, appears in heavy ion data because the hot plasma has a collective geometric shape that is imprinted on the particle emission directions as the plasma expands. In proton-proton collisions, there is no mechanism by which a collective plasma state should form. Two protons simply do not contain enough energy or matter to form a macroscopic fluid. Yet the ridge appears. It has been confirmed by multiple analyses across multiple years and collision energies. Several theoretical explanations have been advanced: color glass condensate in the initial state, small system hydrodynamics, quantum entanglement between partons, but none has achieved consensus. The observation stands, confirmed, without a fully understood explanation. The LHC has produced a measurement that exceeds the explanatory capacity of the best current theories of matter. The extra dimensions of space that theorists propose to explain the hierarchy problem were the next major class of cross predictions waiting to be tested at the LHC, and their absence has closed another large chapter of theoretical speculation. The observation of collective behavior in proton-proton collisions is part of a broader pattern of unexpected results in the high multiplicity sector of LHC physics. When the LHC produces events with unusually large numbers of secondary particles, those events show properties qualitatively different from the average collision. The ridge correlation is the most dramatic example, but there are others. The mean transverse momentum of particles in high multiplicity events is higher than in average events, consistent with the presence of a higher pressure source pushing particles outward. Strange particles, particles containing the strange quark, are enhanced in high multiplicity proton-proton events relative to their rate in average events, and the enhancement grows with multiplicity in a way that resembles the enhancement of strange particle production in heavy ion collisions, where quark-gluon plasma formation is well established. The strangeness enhancement in heavy ion collisions was historically one of the first proposed signatures of quark-gluon plasma formation and was observed at CERN's SPS accelerator before the LHC era. Its appearance in proton-proton events at high multiplicity at the LHC was not predicted and is not fully explained. The ALICE experiment at the LHC, designed specifically for the study of heavy ion physics, has extended these observations with detailed measurements of identified particle species in proton-proton, proton-lead, and lead-lead collisions across a range of multiplicities and collision energies. The picture that emerges from ALICE data is a smooth evolution of collective behavior from the heaviest to the lightest collision systems, with no obvious discontinuity between proton-proton and light-ion collisions that would signal a threshold for quark-gluon plasma formation. This smooth evolution is hard to reconcile with theoretical pictures that predict a sharp threshold above which a plasma forms and below which it does not. It is instead consistent with a picture in which collective behavior is a universal feature of high-density QCD matter at any scale, reflecting the strongly coupled nature of the quark-gluon system, even in tiny volumes and short timescales. The connection between the LHC's heavy ion physics and the string theory ADS-CFT correspondence deserves further elaboration because it represents one of the most unexpected intersections of high-energy physics and theoretical physics in the past 2 decades. The ADS-CFT correspondence, developed by Juan Maldacena in 1997, is a conjecture relating two apparently different mathematical frameworks: a conformal field theory in flat spacetime, which describes the behavior of a specific, strongly interacting quantum system, and a string theory in an anti-de Sitter spacetime with one extra dimension, which describes gravity and string vibrations. The conjecture states that these two descriptions are equivalent. Every calculation done in one framework can in principle be done in the other, and the results must agree. The significance of this correspondence for heavy ion physics is that it provides a tool for calculating the properties of strongly coupled quantum systems in cases where perturbative methods fail. Quantum chromodynamics at the temperatures of the quark-gluon plasma is not weakly coupled despite the intuition from asymptotic freedom. The temperature is high enough to liberate quarks, but not so high that the coupling is genuinely small. In this intermediate regime, neither weak coupling perturbation theory nor the non-perturbative methods of lattice QCD, which works best at zero temperature, is fully reliable. The AD-CFT correspondence offers an alternative. Map the strongly coupled problem onto a string theory calculation involving a black hole, where the properties of the plasma correspond to properties of the black hole's horizon. The viscosity to entropy ratio of the quark-gluon plasma, for example, corresponds in the AD-CFT framework to the ratio of the absorption cross-section to the area of the black hole horizon. When this calculation is done, the result is a universal minimum value equal to a specific combination of fundamental constants. The quark-gluon plasma at the LHC measures remarkably close to this minimum, validating the application of string theory methods to the hot QCD problem. This is not a direct confirmation of string theory as a description of quantum gravity. The AD-CFT correspondence applies to a specific mathematical model, not necessarily to the real-world string theory that might describe gravity at the Planck scale, but it demonstrates that the mathematical tools developed in string theory have genuine predictive and explanatory power in a domain very different from the one for which they were developed. The LHC's quark-gluon plasma measurements represent the most direct experimental contact between string theory formalism and real-world experimental data that currently exists. The practical implications of the quark-gluon plasma measurements extend beyond fundamental physics. The early universe passed through the quark-gluon plasma phase during its first microseconds of existence, and the properties of that phase affected the subsequent evolution of the universe. The transition from the plasma to confined hadrons at a temperature of roughly 150 mega-electron-volts, a few microseconds after the Big Bang, determined how many baryons survived and how they were distributed. The viscosity of the plasma affects the degree to which density fluctuations were damped or amplified during the transition. The precision measurements of the plasma's properties at the LHC directly inform models of early universe evolution, connecting the most powerful accelerator ever built to the cosmological history of the universe. One specific connection involves the production of heavy quark-antiquark pairs in the quark-gluon plasma. Quarkonium states, bound states of a heavy quark and its antiquark, such as the J-psi particle made of a charm-anticarm pair, are suppressed in the quark-gluon plasma because the screening of the strong force by the deconfined quarks and gluons prevents the bound state from forming. This suppression was proposed as a signature of quark-gluon plasma formation and was observed at the SPS before the LHC era. At the LHC, the suppression pattern for different charmonium and bottomonium states has been measured with high precision and compared with models of the plasma temperature profile and the dissociation temperatures of the different states. The results provide detailed information about the spatial and temporal evolution of the plasma beyond simple bulk properties like viscosity. The LHC's heavy ion program is building a quantitative picture of the quark-gluon plasma that connects particle physics measurements to cosmological questions about the first moments of time. Extra spatial dimensions were supposed to appear in LHC data as dramatic signatures, heavy graviton resonances and microscopic black holes, and the systematic non-appearance of these signatures has eliminated large swaths of the theoretical parameter space that motivated their prediction. The Randall-Sundrum model, in its original form, predicted Kaluza-Klein graviton resonances with masses of roughly a few trillion electron volts and decay rates proportional to standard model particle production rates. The first such resonance was expected to appear as a sharp peak in the invariant mass distribution of Drell-Yan events, collisions producing a pair of leptons through virtual photon or Z-boson exchange at masses accessible to the LHC. Run 1 excluded these resonances below approximately 1 trillion electron volts. Run 2 pushed the exclusion to several trillion electron volts. The model's prediction that the lightest Kaluza-Klein graviton would appear at masses solving the hierarchy problem without fine-tuning, masses of 1 to 2 trillion electron volts, has been falsified. The model survives only with parameters tuned to put the lightest resonance above the LHC's sensitivity, which requires reintroducing a fine-tuning that the model was designed to eliminate. The large extra-dimension models of Arkani Hamed, Dimopoulos, and Dvali were tested through searches for deviations from the standard model in high-energy Drell-Yan production, where virtual graviton exchange in extra dimensions would add coherently to the standard model amplitude and produce an enhancement or suppression of the lepton pair production rate at high mass. Searches in the dielectron and dimuon channels at ATLAS and CMS found no significant deviations from the standard model prediction across the full mass range accessible in Run 1 and Run 2. The effective Planck scale in the extra dimension models is excluded below several trillion electron volts for 2 extra dimensions and below several hundred giga electron volts for 6 extra dimensions. These exclusions cover the parameter space where the models most naturally solve the hierarchy problem. The microscopic black hole searches probed both the large extra dimension scenarios and string theory-inspired scenarios where the string scale is near the electroweak scale. These searches looked for high multiplicity events with very large total transverse energy, which is the expected signature of a highly energetic microscopic black hole evaporating democratically into all particle species. The events would be distinctive and hard to mimic, with standard model backgrounds, sudden, explosive production of many particles in all directions, with large missing energy if some of the black hole's decay products are neutrinos or gravitons. No such events were found. The minimum mass at which microscopic black holes must form, if the large extra dimension scenarios are correct, has been pushed above several trillion electron volts, far above the range where the hierarchy problem would naturally suggest they should appear. The systematic elimination of extra-dimensional signatures, in parallel with the elimination of supersymmetric signatures, has left the hierarchy problem completely unresolved by experiment. This is the central fact of the LHC era. The machine was built with the expectation that one or more of the proposed solutions to the hierarchy problem would appear in its data. None has. The hierarchy problem is real. The proposed solutions have been tested, and the solutions are not confirmed. Physicists must either find a new solution, accept that the hierarchy is not a problem to be solved by new particles near the electroweak scale, or build a more powerful machine that can reach higher energies. All 3 paths are being pursued simultaneously. Extraspatial dimensions were proposed not as mathematical curiosities, but as solutions to the most pressing theoretical problem in particle physics. The hierarchy problem, which asks why the Planck energy is 10 million billion times higher than the electroweak energy scale, has motivated theorists since the 1970s to look for a mechanism that would make the enormous ratio natural rather than accidental. Supersymmetry was one approach, extra dimensions were another, and in the 1990s they were developed into detailed models with specific, testable predictions for the LHC. The universe has 3 dimensions of space and 1 of time, as far as all human experience and all experiments have ever been able to detect. You can move in 3 independent directions: forward, left, up, and combine them in any proportion. Time flows in one direction. That is the complete set of dimensions that all physics before the 20th century had to work with. But the mathematics of theoretical physics does not require the universe to limit itself to 4 dimensions. String theory, the most ambitious attempt at a unified description of all forces, including gravity, requires 9 spatial dimensions to be mathematically consistent. The extra 6 dimensions, in the standard picture, are compactified, curled up into tiny geometrical structures at length scales so small that no existing instrument can detect them. This compactification makes the extra dimensions functionally invisible at all energies currently accessible to experiments. In 1998 and 1999, several groups of theorists proposed that extra dimensions might be relevant to string theory at the Planck scale. and also to the hierarchy problem at the electroweak scale. Nima Arkani Hamed, Savas Dimopoulos, and Gia Dvali proposed a model in which two or more extra spatial dimensions have sizes much larger than the Planck length, potentially as large as a millimeter, and gravity can propagate through these extra dimensions while the standard model particles and forces are confined to a three-dimensional surface called a brane. In this model, gravity appears weak in the three-dimensional world because it is diluted by spreading across the additional large dimensions. The true strength of gravity, accessible at the short-distance scales probed by the extra dimensions, would be comparable to the other forces. This would make the Planck energy, as perceived by a four-dimensional observer, much lower than the conventional Planck energy, potentially as low as the electroweak scale, eliminating the hierarchy between scales. Lisa Randall and Raman Sundram proposed a different model in 1999, involving a single extra dimension with a specific geometric curvature, a warped extra dimension. In the Randall-Sundram model, the universe consists of two three-dimensional branes bounding a five-dimensional bulk. The curvature of the extra dimension creates an exponential warp factor that relates the energy scales on the two branes. If the standard model particles live on the low-energy brane and gravity lives primarily near the high-energy brane, the exponential warp factor naturally generates the enormous ratio between the Planck scale and the electroweak scale without fine-tuning. The hierarchy is geometrically explained. This model made highly specific predictions for the LHC, Kaluza-Klein excitations of the graviton, heavier copies of the graviton corresponding to different momentum modes in the extra dimension would appear as sharp resonances in the mass spectra of lepton pairs and photon pairs at masses of a few trillion electron volts. If extra dimensions existed at the scales these models required, the LHC would also create microscopic black holes. When two protons collide with enough combined energy, the energy concentration in the tiny collision volume could exceed the true Planck energy as modified by the extra dimensions. At that point, general relativity predicts that a black hole forms. But unlike the astrophysical black holes that are millions or billions of times the mass of stars, these would be microscopic, far smaller than an atomic nucleus, with masses of only a few times the proton mass. They would evaporate almost instantaneously through Hawking radiation, emitting a democratic spectrum of all particle species in proportion to their statistical weights. This Hawking evaporation would produce a distinctive shower of particles across the detector, identifiable by its multiplicity and energy distribution. Finding such events would be direct evidence for extra dimensions. Both ATLAS and CMS searched for all of these signatures from the beginning of LHC operation. Searches for Kaluza-Klein graviton resonances looked for sharp peaks in the invariant mass spectrum of dilepton and diphoton events. Searches for microscopic black holes looked for high multiplicity events with the characteristic democratic distribution of particle types. Run 1 returned nothing. Run 2, at higher energy and with much more data, returned nothing. The lower mass limits on Kaluza-Klein gravitons in the Randall-Sundram model were pushed above 4 trillion electron volts. The cross-section limits on microscopic black hole production excluded the simplest large extra dimension scenarios across the full mass range accessible to the LHC. The most optimistic and theoretically motivated predictions for extra dimensions at the LHC have been falsified. The hierarchy problem, which the extra dimensions were designed to solve, remains without a confirmed explanation. One by one, the theoretical proposals that would make the hierarchy natural have been tested and found absent. The absence of extra-dimensional signatures, combined with the absence of supersymmetric particles, creates the deepest crisis in theoretical physics in decades. The two leading solutions to the hierarchy problem have been tested at the energy scale they were predicted to inhabit, and neither has appeared. What comes next? What mechanism explains the smallness of the Higgs mass relative to the Planck scale, if it is not supersymmetry and not extra dimensions, is the central unanswered question of fundamental physics. Some theorists have retreated to anthropic reasoning, Perhaps the Higgs mass is fine-tuned, and we find ourselves in the fine-tuned region simply because only in such regions can complex structures and observers exist. Others propose more exotic alternatives, composite Higgs models in which the Higgs is not a fundamental scalar but a bound state of more fundamental constituents, which would naturally protect its mass. Twin Higgs models in which a mirror sector of particles cancels the quantum corrections through a discrete symmetry rather than a continuous one. Neutral naturalness scenarios in which the partner particles that cancel the quantum corrections are neutral and therefore harder to produce at a collider. None of these alternatives has been confirmed. Hiding within all of this lies a stranger puzzle that rarely receives the attention it deserves outside specialized theoretical circles. It concerns not the mass of the Higgs but the internal structure of the strong nuclear force, and it involves a parameter that should be able to take any value between 0 and 6 but appears to be essentially 0 for no reason the standard model can provide. The strong nuclear force is described by quantum chromodynamics, a theory built on the SU3 gauge symmetry of color charge. Quantum chromodynamics is one of the most successful and well-tested quantum field theories ever developed. It explains the confinement of quarks inside protons and neutrons, the spectrum of hadronic particles, the running of the strong coupling constant with energy, and the behavior of quark-gluon plasma. It has been tested at particle accelerators for 50 years and has passed every test. Within the mathematical structure of quantum chromodynamics is a parameter called theta, which appears in a term that can be added to the Lagrangian of the theory. This term, called the theta term, is allowed by all the symmetries of quantum chromodynamics. It does not violate any of the theory's gauge invariances. There is nothing in the structure of quantum chromodynamics that requires it to be 0 or even small. In principle, theta can be any value from 0 to 2 pi, from 0 to approximately 6. A value of order 1, which would be the generic expectation for a dimensionless parameter in a natural theory, would cause the strong force to violate CP symmetry significantly. The neutron, which contains charged quarks arranged in a specific pattern, would develop a measurable separation between its positive and negative charge distributions, an electric dipole moment. Experiments have measured the neutron's electric dipole moment to extraordinary precision. The current best limit places the neutron electric dipole moment below about 3 × 10 to the negative 26 electron centimeters. If theta were of order 1, the neutron's electric dipole moment would be roughly 10 billion times larger than this limit. This means that theta must be less than approximately 10 to the negative 10, smaller than 1/10 billion. A parameter that can range freely from 0 to 6 is constrained to be smaller than 1/10 billionth, with no explanation from the theory for why it should be so small. This is the strong CP problem. The problem is sometimes called a fine-tuning issue, but it is different from the Higgs hierarchy problem in character. The Higgs hierarchy problem involves an enormous cancellation between large quantum corrections. The strong CP problem involves a parameter that is simply very small, with no known reason. From a philosophical standpoint, both cases indicate that the standard model is missing an explanation, a deeper structure that would make the observed smallness natural rather than accidental. The most elegant resolution was proposed in 1977 by Roberto Pecce and Helen Quinn, who introduced a new global symmetry into the theory. This symmetry, when broken, dynamically drives theta to 0, regardless of its initial value, through a mechanism that adds a new degree of freedom to the theory. Frank Wilczek and Steven Weinberg independently recognized that the breaking of the Pecce-Quinn symmetry must produce a new light particle, which Wilczek named the axion. The name was borrowed from a brand of laundry detergent because, as Wilczek explained, the axion would clean up the strong CP problem. The axion has extremely small mass, determined by the scale at which the Pecce-Quinn symmetry breaks, and interacts with ordinary matter primarily through its coupling to photons in the presence of a magnetic field. The axion's most remarkable property, beyond solving the strong CP problem, is that it could simultaneously explain the dark matter. Axions produced in the early universe through the misalignment mechanism, a process in which the axion field is displaced from its 0 theta value when the Peck-Quinn symmetry breaks and then oscillates around 0, with the oscillation energy contributing to the dark matter density, would survive to the present day as a cold, diffuse sea of extremely light particles filling the universe. For a range of Peck-Quinn breaking scales, the axion density produced by this mechanism naturally matches the observed dark matter density. An axion that solves the strong CP problem also automatically produces dark matter of the right abundance. This double coincidence is theoretically compelling in the same spirit as the WIMP miracle, and unlike the WIMP, the axion has not yet been experimentally eliminated. CERN's dedicated axion experiment, the CERN Axion Solar Telescope, operated for over a decade, searching for axions produced in the interior of our nearest star. The solar core produces photons in enormous numbers, and in the intense photon bath, axions would be produced through the Primakov process, a photon interacting with the electric field of a charged nucleus and converting into an axion. These solar axions would stream outward through the solar plasma, traverse the vast distance of space between us, and pass through the Earth almost without interaction. When they entered the intense magnetic field of the CAST apparatus, a decommissioned LHC dipole magnet pointed precisely at the Sun, a small fraction would convert back into X-ray photons, detectable by a sensitive camera at the end of the magnet. CAST found no axions. The experiment set constraints on the axion-photon coupling that, combined with astrophysical limits from stellar cooling, substantially narrowed the parameter space. The successor experiments, Baby IAXO and the full International Axion Observatory, will probe the parameter space, where the most theoretically motivated axion models make firm predictions. Microwave cavity experiments, ADMX, Haystack, Organ, CAP, and several others, search for the conversion of galactic halo axions into microwave photons inside tunable resonant cavities in strong magnetic fields. These experiments are sensitive to different axion mass ranges and are progressively extending their reach into the well-motivated parameter space. As of 2025, no confirmed axion signal has been reported. The axion remains the most theoretically compelling undiscovered particle in physics. It solves two major problems simultaneously. It makes specific testable predictions, and the experimental search is advancing. Finding it would be one of the most significant discoveries in the history of physics. While the axion search proceeds in magnetic cavities and solar telescopes, the Standard Model presents another mystery that is visible in the simplest structural feature of its particle catalog: the existence of 3 generations of quarks and leptons, with masses spanning orders of magnitude that the theory cannot explain. The Standard Model arranges its 12 matter particles into 3 generations of 4, each generation containing an up-type quark, a down-type quark, a charged lepton, and a neutrino. The first generation contains the up quark, down quark, electron, and electron neutrino. These particles make up essentially all ordinary matter. The hydrogen atom consists of 2 up quarks and 1 down quark in each proton, orbited by an electron. Everything made of atoms is made of first-generation particles. The second generation contains the charm quark, strange quark, muon, and muon neutrino. These particles exist briefly in high-energy collisions, in cosmic rays, and in particle accelerators, but decay quickly back to first-generation particles. The third generation contains the top quark, bottom quark, tau, and tau neutrino, heavier still, also unstable, also ultimately decaying to first-generation particles. The Standard Model does not explain why there are 3 generations. It provides no mechanism for generating them, no selection principle that would produce exactly 3 rather than 2 or 4. They were discovered experimentally one by one. The muon in 1936, the strange quark in 1947, the charm quark in 1974, the tau in 1975, the bottom quark in 1977, the top quark in 1995. Each discovery added another row to the table of particles. The pattern was recognized before an explanation was available. The explanation still has not been found. The mass pattern across the 3 generations is even more mysterious. The electron has a mass of approximately 0.511 mega-electron volts. The muon has a mass of 105.7 mega-electron volts, 207 times heavier. The tau has a mass of 1,777 mega-electron volts, 17 times heavier than the muon. For quarks, the hierarchy is more extreme. The up quark has a mass of roughly 2 mega-electron volts, while the top quark has a mass of approximately 173,000 mega-electron volts, making the top 85,000 times heavier than the up. Both are described by the same type of quantum field in the Standard Model. Both are spin 1/2 quarks with coupling to the same 3 gauge forces, yet their masses differ by a factor of 85,000. The Standard Model encodes this difference by assigning different numerical coupling constants to each quark's interaction with the Higgs field, but it provides no deeper reason for why those coupling constants have the ratios they do. The mass hierarchy of the quarks and leptons is an observed fact that the Standard Model describes but does not explain. Precision measurements of the quark mixing angles, the CKM matrix, at the LHC are beginning to show tensions with the unitarity condition that the Standard Model requires the matrix to satisfy. If the matrix elements do not satisfy the unitarity constraints, it implies the existence of additional particles that mix into the quark sector and distort the observed pattern. Some combinations of measurements show 2 to 3 sigma tensions with perfect unitarity. These tensions have attracted increasing attention as the measurements have become more precise, though they are not yet at the level of statistical significance required to claim evidence for new physics. They are, however, consistent with the broader pattern of anomalies, suggesting that the 3-generation structure of the Standard Model may be an approximation to a more complex underlying structure. At the heart of the 3-generation mystery are the neutrinos, which have provided the only direct experimental proof so far that the Standard Model is incomplete, and whose properties remain among the least well understood in particle physics. Neutrinos were hypothetical particles for 26 years before their direct detection in 1956. Wolfgang Pauli proposed them in 1930 to explain the apparent violation of energy conservation in nuclear beta decay. The electron emitted in beta decay carries away less energy than the nuclear mass difference would allow, and Pauli proposed that the missing energy was carried by an undetected neutral particle. The neutrino was detected experimentally by Frederick Reiners and Clyde Cowan in 1956, using the intense anti-neutrino flux from a nuclear reactor to induce inverse beta decay in a liquid scintillator detector. For decades afterward, neutrinos were treated as massless in the Standard Model, their mass constrained to be 0 by the structure of the weak interaction terms in the theory. The 1998 announcement from the Super Kamiokande experiment changed everything. Super Kamiokande, a cylindrical tank of 50,000 tons of ultra-pure water buried in a zinc mine 1 kilometer underground in Japan, had been measuring the flux of atmospheric neutrinos produced when cosmic rays strike the upper atmosphere and produce pions that decay into muons and muon neutrinos. The expected flux of muon neutrinos from below, those that had traveled through the entire Earth, was substantially lower than the flux from above. The neutrinos were disappearing during the passage. They were transforming from muon neutrinos into tau neutrinos, a process called oscillation that can only occur if neutrinos have mass. Massless particles traveling at exactly the speed of light cannot oscillate between flavors because the phase relationship between mass eigenstates that drives oscillation does not evolve for massless particles. The oscillation required mass. Neutrinos have mass. The Standard Model was proven incomplete. The 2015 Nobel Prize in Physics recognized the discovery, awarded to Takaaki Kajita of Super Kamiokande and Arthur MacDonald of the Sudbury Neutrino Observatory in Canada, which had independently confirmed neutrino oscillation through a different approach, measuring the total flux of all neutrino flavors from the Sun versus the electron-neutrino flux only, and finding that the deficit of solar electron neutrinos reaching Earth was exactly compensated by the presence of muon and tau neutrinos, confirming that electron neutrinos were oscillating into other flavors during the 150 million kilometer passage from the solar core to Earth. How neutrinos acquire mass involves physics beyond the Standard Model. The original formulation of the Standard Model contains no right-handed neutrinos, no chirally flipped counterparts to the observed left-handed neutrinos, and without right-handed neutrinos. Mass terms for neutrinos cannot be written in the Standard Model's mathematical framework. The theory must be extended. The most natural extension introduces right-handed neutrinos, which do not participate in any of the Standard Model's three-gauge forces. They would interact only through gravity and through their coupling to the Higgs field, making them essentially undetectable with any current technology unless produced at very high energies. The most elegant mechanism for generating neutrino mass through right-handed neutrinos is called the seesaw mechanism. The ordinary neutrinos we observe are left-handed and light. The right-handed neutrinos are heavy, potentially very heavy, with masses perhaps as large as 10 to the 15 giga-electron-volts, comparable to the grand unification scale. The observed neutrino mass is inversely proportional to the right-handed neutrino mass through the seesaw relationship. As the right-handed neutrino mass increases, the observable neutrino mass decreases, like opposite ends of a seesaw. This explains why the observed neutrino masses are so much smaller than the masses of the other fundamental fermions. The neutrinos are light because their right-handed counterparts are extremely heavy. The seesaw mechanism connects the mass scale of neutrino physics to the grand unification scale, suggesting a deep connection between the lightest known massive particles and the highest energy scales in theoretical physics. The seesaw mechanism also enables a cosmological mechanism called leptogenesis, in which the heavy right-handed neutrinos decay in the early universe with CP violation, producing an asymmetry between leptons and antileptons. This lepton asymmetry is subsequently converted into a baryon asymmetry, a matter excess, through electroweak processes that violate baryon number. If leptogenesis occurred, then the matter we are made of owes its existence to the CP-violating decay of extremely heavy neutrinos in the first trillionth of a second of the universe's existence. Leptogenesis is theoretically elegant. It solves the matter-antimatter asymmetry problem, using physics that is naturally connected to the neutrino mass problem. But it is essentially impossible to test directly because the right-handed neutrinos in the standard seesaw mechanism are too heavy to be produced at any foreseeable collider. The most direct experimental test of neutrino mass physics is the search for neutrinoless double beta decay. In ordinary double beta decay, two neutrons in a nucleus simultaneously convert to protons, releasing two electrons and two electron antineutrinos. The process has been observed in several nuclei and is described by the Standard Model. In the neutrinoless version, the two emitted antineutrinos are reabsorbed by each other inside the nucleus, which is possible only if the antineutrino is identical to the neutrino, meaning neutrinos are Majorana particles. Only two electrons emerge. The signature is a sharp peak in the electron energy spectrum at the full energy of the nuclear transition, with no missing energy from escaped neutrinos. The signal is unmistakable in principle. In practice, detecting it requires an experiment with an extremely small background rate and an enormous quantity of candidate isotope, because the predicted half-life for the decay is extraordinarily long. The Kamlan-Zen experiment, operating in a mine in Japan, dissolves enriched xenon 136 inches, a liquid scintillator, and searches for the distinctive double electron signal. The current world best limit on the half-life of neutrinoless double beta decay of xenon 136 exceeds 2 times 10 to the 26th years. That number is difficult to comprehend. The age of the universe is approximately 1.4 times 10 to the 10th years. The limit on the half-life is more than 1 quadrillion times the age of the universe. The process has not been observed, but this does not rule it out. The predicted half-life, depending on the Majorana neutrino mass, could be anywhere from below current sensitivity to well above it. The next generation of experiments, NEXO, a ton-scale liquid xenon experiment proposed for operation in the SNOLAB underground laboratory in Canada, and Legend 1000, using germanium-76 enriched to high purity, will push the sensitivity to half-lives approaching 10 to the 28th years, covering the parameter space where the neutrino mass hierarchy and Majorana nature predictions overlap in the most theoretically motivated way. If either experiment finds the decay, it will confirm the Majorana nature of neutrinos, establish lepton number violation as a fact of nature, and validate leptogenesis as the mechanism behind matter's dominance. That would be the most consequential experimental result in particle physics since the discovery of the Higgs boson, and possibly since the discovery of CP violation in 1964. The LHC entered run 3 inches, April 2022, with a record proton-proton collision energy of 13.6 trillion electron volts, established through improvements to the accelerating cavities and the beam injection sequence. The luminosity, the rate of collisions per unit area, also reached record levels, with both the ATLAS and CMS experiments recording unprecedented numbers of collision events per second during peak operation. By the end of Run 3, expected in 2026, the total accumulated proton-proton collision dataset will exceed the combined total of all previous LHC runs. This expanded dataset is being analyzed simultaneously by thousands of physicists pursuing hundreds of independent analysis strategies. In the Run 3 data, both ATLAS and CMS have found excess events in the Dittau channel near 100 giga-electron volts. The local significance in each experiment is at the 2 to 3 sigma level, and the observation of an excess at the same mass in the same channel by 2 independent detectors is harder to attribute to coincidental fluctuations than a single experiment excess would be. The 100 giga-electron volt mass region is theoretically interesting for several reasons. Many extensions of the standard model predict a second, lighter Higgs boson. In the minimal supersymmetric standard model and various non-minimal variants, additional scalar particles appear alongside the 125 giga-electron volt Higgs. Some of these additional scalars are predicted to have masses in the range of 90 to 110 giga-electron volts, and to couple preferentially to tau leptons. Axion-like particles from Peccei-Quinn symmetry breaking at a relatively low scale could also produce signals in this region. The excess is being watched carefully as more Run 3 data is analyzed. Whether it grows to discovery significance or dissolves like the 750 giga-electron volt excess will be known within the next few years. The high luminosity LHC upgrade will transform the machine's capabilities beginning around 2029. New superconducting focusing magnets will squeeze the proton beams to smaller cross-sections at the collision points, increasing the luminosity, the collision rate per unit area, by a factor of 5 to 10 compared to current operation. New crab cavities will tilt the colliding bunches to maximize the geometric overlap, further increasing the effective collision rate. By the end of the high luminosity LHC program in the late 2030s, the total accumulated integrated luminosity will be approximately 10 times larger than what Run 3 will deliver. This expanded dataset will allow measurements of Higgs boson couplings to percent-level precision, searches for extremely rare processes like the Higgs decaying to a photon plus a Z boson at high precision, and sensitivity to new particles, and forces extended to rates many times smaller than currently accessible. Any anomaly in the current dataset that is real will grow to discovery significance with the expanded statistics of the high luminosity LHC. Any anomaly that is a fluctuation will dissolve. The machine will answer the questions currently sitting at 2 to 3 sigma definitively. Beyond the high luminosity LHC, the physics community is engaged in a debate about the next generation of instruments that is as consequential as any in the history of science funding. The Future Circular Collider, proposed at CERN and developed in a comprehensive feasibility study, would require a new tunnel 91 kilometers in circumference buried beneath the Franco-Swiss Jura region. In its first phase, FCC-E, it would operate as an electron-positron collider at energies spanning from 90 giga-electron volts to 365 giga-electron volts, producing enormous samples of Z bosons, W bosons, Higgs bosons, and top quark pairs for precision measurements. The Higgs coupling to each particle species would be measured at the fraction of a percent level. Any deviation from standard model predictions would be visible at that precision, even if the new physics responsible lies at mass scales of tens of trillions of electron volts. In its second phase, FCCHH, the same tunnel would house a proton-proton collider operating at 100 trillion electron volts, nearly 8 times the LHC's current energy. At that energy, particles with masses up to roughly 40 trillion electron volts could be directly produced. The dark matter candidates, new Higgs bosons, Z-prime bosons, leptoquarks, and whatever is responsible for the hierarchy problem that are too heavy for the LHC could be within range of the FCCHH. China has proposed an alternative first step with the Circular Electron-Positron Collider, which would explore the same physics as FCCE at similar energies. Japan's proposed International Linear Collider offers a linear electron-positron machine at 250 giga-electron volts, emphasizing Higgs factory measurements in a different design. The decisions about which of these facilities to pursue will shape the direction of fundamental physics for the second half of the 21st century. The standard model contains 19 parameters that must be measured rather than derived. 6 quark masses, 3 charged lepton masses, 3 mixing angles, and 1 CP violating phase in the CKM matrix. 3 mixing angles and 1 CP violating phase in the neutrino mixing matrix. 3 gauge coupling constants for the 3 forces: the Higgs mass, the Higgs vacuum expectation value, the vacuum energy density, sometimes listed separately. These are inputs to the theory, not outputs. A fundamental theory would derive them from mathematical principles the way Bohr's model derived the hydrogen energy levels from fundamental constants. The standard model cannot. It accepts whatever values are measured and uses them to make predictions for other observables. This is the characteristic behavior of an effective field theory, a description that is accurate within a limited domain of energies and phenomena, but breaks down at some higher scale where the underlying fundamental theory is needed. The standard model will break down. This is not speculation. The hierarchy problem tells us that new physics must appear at some scale above the Higgs mass. The dark matter tells us that particles exist outside the standard model. The matter-antimatter asymmetry tells us that CP-violating processes exist beyond those in the standard model. Neutrino mass tells us that right-handed neutrinos, or a Majorana mass mechanism, exists beyond the standard model. The strong CP problem tells us that the Peck-Sequin symmetry, or some equivalent mechanism, exists. Each of these facts independently demands extensions to the standard model. Together, they form a compelling case that the standard model is an approximate description of a deeper theory, and that the deeper theory contains particles, forces, and symmetries that have not yet been observed. The LHC's role in this context is to probe the energy frontier where the breakdown of the standard model's approximations is most likely to become visible. The machine has done this faithfully. It has confirmed the Higgs boson and measured its properties. It has searched systematically for the new particles predicted by the leading theoretical extensions. It has found persistent anomalies at specific significance levels in specific channels. It has produced conditions that exceed any prior experiment and revealed unexpected properties of matter at extreme temperatures. What it has not done is conclusively identify the physics that lies beyond the standard model. That identification may require more data, more analysis, or a more powerful machine. The answer is not yet in. History counsels patience along with urgency. The prediction of the Higgs boson in 1964 was confirmed experimentally in 2012, a gap of 48 years. The prediction of the W and Z bosons in the 1960s was confirmed in 1983, about 15 years. The prediction of the top quark in 1977 by Kobayashi and Maskawa was confirmed in 1995, 18 years. In each case, the experimental confirmation required building a machine more powerful than anything that had previously existed, and each machine took years or decades to design, fund, and construct. The theory knew the answer was there. The experiments had to reach it. The current anomalies are telling physics that something is there at specific confidence levels in specific channels. Reaching it requires either more data from the current machine, a new machine, or both. Every civilization that has penetrated to a new layer of physical reality has found something unimaginable from the layer above. 19th century chemists studying the periodic table of elements could not have imagined that atoms had internal structure, or that the structure would involve quantum mechanics, or that understanding quantum mechanics would eventually produce lasers, transistors, and nuclear reactors. The physicists who discovered atomic structure in the early 20th century could not have imagined that the atomic nucleus itself had internal structure, or that the nuclear strong force would require an entirely new kind of mathematics, non-abelian gauge theory, to describe. The physicists who discovered quarks in the 1960s could not have anticipated the Higgs mechanism, the precision measurements of LEP, or the extraordinary confirmation of quantum chromodynamics at the LHC. Each layer of discovery was rich beyond what the previous layer had suggested. The layer beyond the standard model will be the same. The protons circling in the LHC tunnel right now are the most precisely controlled objects in history. Each one carries a kinetic energy roughly equivalent to a flying mosquito, small by human standards, but enormous for a single proton. 11,000 of them circle the 17-mile ring every second, 40 million times per second. Bunches of 100 billion protons cross inside the detector caverns, and from 100 to 1,000 collisions occur in each crossing. Every collision is an experiment. Every record of the debris is a measurement. Every comparison between the measurement and the standard model's prediction is a test. And in that test, in the specific, reproducible 5 sigma and 7 sigma and persistent 3 sigma deviations from what the theory predicts, something is making itself known. The shape of that something has been outlined by decades of experimental work. Its precise nature is the outstanding question of the era. The machine in the tunnel is asking it. The answer is coming, and when it arrives, it will change everything that follows it, in the way that every discovery at every previous depth has changed what came after. The universe has been operating according to whatever the answer is for 13.8 billion years. Physics has been organized well enough to ask the right question at the right precision for less than a century. The gap between those timescales should not be discouraging. It should tell you how early we are, how much remains, and how extraordinary it is that a process called human physics, running on a planet around an ordinary star in one of hundreds of billions of galaxies, has reached the point where it can hear the universe beginning to answer.